All right, I'm going to be talking about, or rather, hi, my name is Max. Some of you might know me. I'm going to be talking about fuzzing, so let's do this. So what is fuzzing? Fuzzing is the idea that we want to look at programs and we want to look at input to those programs. We want to try to break programs, giving them input that they don't use. And a lot of you run into this when you're writing code. You're taking in some command line arguments, and if someone gives you an evil one, everything explodes, and we're basically just trying to make everything explode. It's the general goal. And when I say explode, I mean like memory errors in your C programs, I mean like your web application not sanitizing some search parameter, etc. Just malicious input, and finding that in an automated way. So what can we fuzz? We can fuzz basically anything that takes input and a lot of things that don't take input. I saw a really cool setup once, which was a controller connected to a bunch of little embedded devices, each of which had a small buffer of memory on them. The controller's job was to swoop through and collect that data every like 300 milliseconds or something. And so the setup was that we had another controller that would just fill these buffers with garbage every once in a while, or fill one or more of them, and just see if the controller on the other end just died at any point, which it did a lot. The programmers were like, yeah, these buffers will all be totally parsable as like valid strings, right? Yeah, sure. And so that didn't happen. And because we can fuzz anything that takes input and most things that don't, this is a really big universe of things that we can target with fuzzing. And then some of the more classic examples, command line utilities, we'll look at some of those later. And basically anything, data coming in over the wire, data coming in over HTTP, anything that takes input. So yeah. And so what we're going to learn is we're going to learn how we fuzz things. And the way we do that is, as you can see, this cat is an expert, very knowledgeable in things related to fuzzing. So you could do that, or you could use some tools. And there's a lot of really shitty fuzzing tools, like really garbage ones. And then there's kind of a lot of domain-specific ones. You might have one that's specifically targeted towards generating like cross-site scripting payloads, or one that's specifically targeted towards generating SQL injection payloads. But when we're talking about just generic fuzzing, especially with what we'll get into, we want to look at just kind of data and structured data, and how we're going to play with that to fuzz applications. Okay. So we're going to do demo number 1, which hopefully will go well. So I'm going to just kind of go ahead with this one, and things will become apparent later. Robert? Yes.
Do you want to increase the text size of the
Yeah. Okay, let's get, can I mirror this? I swear I can mirror this. Okay, we're not going to worry about that. It's not worth it.
Probably should have you.
It might be right. Control plus. That's really confusing. All right, we good? Yeah, can we see? Okay. Oh my God. All right, we can see. So theoretically, I wrote a makefile, so I can just do this. Yeah, we did.
Make sure people know it's 1 and 7. Yes.
So AFL has a UI that doesn't like to be made that big. We can make it just about this big. So what we've got going on here is we've got this is the user interface for AFL. There's a lot going on. We're not going to go over all of it, but one thing that is cool to note is that we see on the top right we have crashed the program once, and we're running it about 2,500 times per second, which is pretty neat. And as you can see here, it's crashing a whole lot. So now let's look at just some of the stuff that entails. So that was a lot of some flashing text. So let's go over what happened. First, what we did earlier was that I compiled my C program with AFL GCC. What that is there's also AFL Clang if you're into that. So what that did was that rolled through my C program and put a bunch of markers on the code paths and the places that read input. And that was for basically just detecting which code paths are being taken, which is kind of neat when you think about it. Like they wrote a custom, or Zalewski we'll talk about, wrote a custom compiler build just to tag your code and intelligently figure out where in your code stuff is going to happen, and then when you're running the fuzzer, try to cause those things to happen. We give it an input test case. This program was a very simple program. I can show it to you. It read in a character, and if that character was 1, it called a function which just went ahead and segfaulted. And so otherwise it just walked right along. And so this is obviously a really simple case. We gave it in my test case, which I'll show you, was just I think a 0 or something like that. Yeah, test case was just a 0. So what AFL did was it took that test case and ran it and was like, okay, so this is what it looks like. This is what a clean run looks like. And then it started playing with that file, the contents of that file, and just messed with them in ways that we'll get to. And caused, at least one of them must have been interpreted as a 1 because it, as you saw, it caused the program to crash. But it did detect that there was only one unique crash, because this is really only one code path that leads to that crash. Okay. And things did explode. The thing was segfaulting. I think it segfaulted 400 times is what we saw there. So yeah. But we're going to answer the second question, which is also important, which is that AFL is the American Fuzzy Lop. And that is a breed of rabbit, importantly. It is also the fuzzing tool that we were just using, written by Michael Zalewski, who is amazing. He was just kind of like, I think I'm going to write a fuzzer. And then a month and a half later, was like, hey guys, here's AFL. And then it became the industry standard for binary fuzzing. He also went, I'm going to write a web application scanner, and wrote it in like 2 weeks, and it became canon as well. And he did the same thing with a book, which is called Tangled Web, which is definitely worth reading if you are interested in browser security. But to explain the bunnies, we could have pictures of Michael Zalewski scattered throughout this slideshow, but bunny's computer. So we're going to do bunnies. Okay. So yeah, next up we're going to talk about the genetic algorithm that goes into AFL, which sounds scary and is cool. So genetic algorithms are kind of loosely defined by a composition of a few parts. One is a genetic representation, so that's anything from like some super complex like natural language representation to like a binary tree to what AFL uses, which is a essentially just byte representation. I like to think of it kind of like regex. But it's a bit more complicated than that and a bit less human readable than that. And so yeah, we'll get that excited. It's also made up of a fitness function, which we'll talk about, and a set of basic operations, which generically are defined as crossover and mutation, but in the AFL implementation are actually like bit flip, add byte, delete byte, mangle, tokenize a string, and then repeat it and play with it, and just kind of all of this manipulation of the input files. So yeah, we have our genetic representation. I put a regex down here that would match like any PHP program. I'm sure it's horribly broken. But like we have the opening PHP tag, a new line, any alphanumeric characters, and then some semicolons, new lines, tabs, whatever. That any number of times, and then a new line, and then a closing parameter, right? So this is a representation. We could call this a representation of all PHP scripts. And so what is amazing about AFL is that it reads in a basic PHP script, for example, and then figures that out based on the script, and uses that as its fuzzing domain, which is awesome. Yeah, I'm sure you can read that. Cool. So then we have the fitness function, which is we want to take these inputs and we want to essentially categorize them and figure out what to do next based on what behavior that input caused. And so for AFL, our fitness function is, well, did we break the program? Because that's in the end, the goal of this is to cause like a memory or basically the program to be ended with an abnormal signal. And so AFL will take in your input and your clean input, run it, and that should run just fine. Then it'll go, okay, so can we use our basic operations to modify this? Okay, are different code paths triggered if we modify this in a certain way? And every time it figures out a new code path, it kind of bookmarks that and modifies that later. Every time a new crash is created, it saves that for you. And yeah, essentially we're just kind of like modifying and checking, modifying and checking, modifying and checking it, so that your test case bed kind of grows naturally out of what the algorithm figures out to give the program. And interestingly, before I move to this slide, is the code paths thing, which is something that very few other fuzzers have. Because it rolls through, it marks each code path during compilation, it can figure out the code coverage of the fuzzing, which is awesome, because you want good coverage. So when we're giving a binary, we're talking about binary data. We're talking about basically random inputs. These are going to grow in unpredictable ways. And so the way that AFL does that is essentially, like I said, generates that template based on your inputs, and then just starts messing with it. And as we'll see, that can cause some explosions in things that people have thought are robust. And this is available. Blah 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 blah. Okay, so this is a massively tiny massively tiny guy. Okay, this is a subset of the things that AFL has found exploitable memory bugs in, which is amazing because like less is on that list, and every single Linux file system implementation that has existed, at least like the popular ones, which was bajillions. TCP dump, the thing that reads network packets going on over the wire. So like, someone can send you a malicious packet and then TCP dump just dies. OpenSSL, no surprise. OpenSSH, terror, that's no good. And if you go to their page, you can see like, there's this huge wall of just all of like the kill list. And each one has like one or more annotations that are links. OpenSSL has like 7. OpenSSH has like 9. It's no good. Like just all of these high-risk CDs that have come out of fuzzing. NTP is on there. Actually, AFL was what was used to find. If you may have noticed, this was like a year and a half ago maybe. If you have a MacBook, it would have done a forced reboot update, which is the only time they've ever done that, which was to update the network time protocol daemon when a remote code execution exploit was found in the NTP listener, which means that you could just take over everything. So this is like an awesome list, and the list goes on and on the website, which is just beautiful. And it just kind of shows that AFL is amazing in practice. So we're going to do another demo. This one will hopefully be a little cooler than just like the super simple one. So now that we know what AFL is doing, there we go. Yeah, okay. So actually, let's take a look at this program first. Better not use less. So we've got an ancient version of libxml that we built locally and are using here. This is basically just going to pull in a file and parse it and validate the XML, which is of course a perfect use case for AFL. It's reading directly reading in a file and manipulating it. And so in our test case, we've got just a valid, simple, there we go. Super simple bit of XML found on the internet. And so that gives it a notion of what a valid XML file looks like. And so from there, it'll just like go crazy with it. And we can look at, also just note that anything exploitable that this spits out is your net. So what it's going to do is, we can take a look at some of the test cases that it spits out, but it's just going to work with that one very simple one. Modifying the opening and closing delimiters, modifying the content in the middle, kind of figuring out what the valid character set is based on how the program treats the file. And we can talk a little bit more about this UI now that we kind of have some introduction. You can see it's forking off and execing about 1,000 of these per second, super quick, giving us some timing information every time it's found a new code path or just the total runtime. The overall results, we can see it's caused 2 hangs so far, which is kind of neat. Those might not be exploitable, but they're edge cases in the program that maybe we would look into further. And we've got kind of some more information about the code paths, and then the map coverage has to do with the internal representation of all of the different code paths, the kind of code path tree, and how much of that is being kind of effectively fuzzed. Fortunately, with very simple ones, that often doesn't get very simple programs like this. It doesn't get super high up there just because you've got a giant library and then a very small subset of code that's getting touched. And like you saw, this basically pulls in one function from the entirety of XML and runs it. And so it's not getting great map coverage. There's some things on here and I still don't know what are, but I'm sure they're useful. So we caused some hangs, and now we can look at kind of what this is doing for us. Have a nice day. Okay, so if we look at the outputs, we get some nice data, we get some statistics, and then crashes, hangs, and the future test queue that we didn't get to. If we look at some of the hangs, we can see, okay, we've got 2 files in here because there were 2 unique hangs. It's telling us the operations that it did. It's saying, okay, well, we treated, I don't know this language entirely, but it looks like we stuck in an int max into position 11 here. And here, similarly, it looks like we added a byte in there. And then we can cat these and see exactly what the content of them is. Okay, so we've got some data. This is it took that valid XML file you saw and actually just generated this based on its own internal representation and caused a hang. I have no idea how it got there, because what happened there was basically it just kind of started figuring it out. And it's kind of hard to conceptualize in that sense, just because what it's doing is so weird, but it is effective, as we saw. Yeah, so we've got, it looks like the start of a valid XML file, and then maybe a broken tag and some weird bytes. Some strange non-ASCII in there.
The first one seems to be a little more obvious. It changed that to just some random.
Yeah, some Unicode garbage.
Well, the first one you have in the very bottom, the next one.
Oh yeah.
You see that in the 2 field?
Yeah, for sure.
Right, first one did a no byte, 1 byte.
Cool. Yeah, so you can with similar cases you can start to kind of pull it apart and see what that looks like, which is kind of nice. And it's also just really nice to have all of this so that when you're done, you can check it out. I believe that this one also has a graph. So what we do here is that AFL will also generate some nice data for us about our exploitation. And this is mostly just like performance information, but it's kind of neat. It looks cool. Anyway, I like that. All right, so let's go on. Let's move on. Okay, so what I want to run after this it's just a third demo, but one that is likely to explode. I haven't run this one yet, so I don't actually know what's going to happen. But it's an old version of a couple of bin utils, including readelf and strings. And so if we see those explode, unfortunately it won't be 0 days, but like, you know, it'd be fun to see some explosions. But I also want to, while I get this running, field any questions that you guys have.
So it's basically taking your sample input and using that to characterize the kinds of input that the program expects to see.
Mm-hmm.
That's crazy. So in
Yeah.
addition to just fuzzing, you can also do this to reverse engineer some program that you have to compile it. But I mean, if you wanted to reverse engineer something that I had the code for already.
Yes.
Like if you didn't feel like reading the code, you could still come up with a description of what the program expects to see as input.
Yes.
And then compare that against what you believe you made the program expect. So it's another way to compare what you programmed with what you think you programmed.
Yeah.
You're checking for edge cases, essentially.
Yeah.
Mm-hmm. Yeah.
I think there's obviously other fuzzes out there, but with was it ALF? Or
AFL.
With AFL, can you run it even if you didn't compile it? Just take out the part where it does the
So
coverage?
yes, it will actually work on those are called uninstrumented binaries, just not as well.
Well, yeah, you don't get the code coverage.
Exactly.
But you
It
can
will try and do its best, and it does turn up a lot of cool stuff, but it's slower and a little less effective. But yes, it absolutely does. It does something with QEMU stub domains to create a clean environment to work your program in, and I'm really not sure how that works, but I'm sure it's neat.
So is this like,
Right.
is this like a machine learn, like is it doing straight up machine learning or?
Essentially, it's a genetic algorithm that you could call machine learning.
It's
It's just so.
Checking crashes.
Oh, cool. This is readelf. This is the GNU implementation of a C program which is designed to parse Linux executable files. Yeah.
So if I recall correctly, in this process, it also does some interesting things to try to minimize the crashing input, doesn't it? Say,
Yes.
this thing crashes, can I find a smaller thing that's like it and still crashes?
Yeah, there's
Nice small.
it does that in process. It also offers a tool to do that further.
Sure.
So you can take test cases and reduce them, and just kind of run that on your own. It also attempts to do that when it's because when it finds a crash, it kind of it weights that input very highly, and then then that input and various modifications of that input will come around the queue much more often, and so as part of that, reductions of that input will come around. But yes, it tries very hard to give you the minimal input that will cause the same unique crash.
That's exactly what I was.
Yeah. Yeah.
Where will they use this in industry particularly?
So you use this in industry on basically programs that you really, really depend on. If you're like flight control code takes an input from like a sensor. If that sensor goes haywire, breaks, or goes rogue, you want to make sure that maybe you don't, it's not ideal because you can't collect data from that sensor anymore. You really don't want it to crash your command and control infrastructure. Because if a sensor goes rogue, you want it to explode the entire system and have a rippling effect, crash the plane. You want it to just have a bad sensor. So this is some old code. This is like some 1999 code. But 52 unique code path crashes is pretty sweet, especially in a program that's meant to read. So this is this program is meant to read a strict format, it's meant to read ELF. And so it's kind of less surprising that we have crashes. But what if we look at a program that is meant to read anything? So what this is strings, which I'm sure many of you have used in your reversing, which is literally meant to handle anything you throw at it and then parse out the valid C strings in it and print them for you. And so you would think that like this would be pretty stable, and, like could handle some input, but you would be wrong.
How old some test cases are big? How old is this?
And there you go.
Yeah.
This is the 1999 Bin Use Hills version 2 point something, 2.13. I know that's the version of Fuzzy Lop, but I think it's also the version I picked of
What's your sample?
Bin Use Hills. What's that?
What's your sample input on?
The sample for strings.
Yeah.
It's actually the same compiled binary I handed to readelf, which just contains a string that says hi. And so yeah, we got four crashes, and we don't know at this point whether those are exploitable or not, but more than likely, one of them is a buffer overflow, which means more than likely we can get at least some sort of complex attack against this binary.
So the outputs, they tell you, I mean, obviously you could probably figure it out by running the input again, but do they tell you like which code branch went down? It's sort of tracking that.
You know, I believe it does. There's an AFL analyze function that it offers you, and I haven't played with that one yet, but yes, I think for an instrumented binary you can do that. It'll also give you crash. Well, you can just run the thing again and get a crash dump. Oh, that's the, yes. So the answer is no, you just run it against the compiled program and see where it crashed, either with, any of your debugging tools, GDB, Valgrind, whatever you like.
It sounds like ELF is only compatible with kind of the C family for AFL.
So yes, it does. It offers AFL GCC and AFL Clang. It also offers AFL G++. And if you look at which is actually just like a superset of GCC. And if you look at everything that GCC can do, it can compile everything from like Fortran to Objective-C.
Yeah.
And so you do have options. I believe it was built out to support most of this. So yes, the C family, but yeah.
So what kind of fuzzers exist that support things that don't exist in the C family?
If you want me to name some fuzzers, I would say.
Or just like, do they mostly like aim to do the similar thing, or is there anything particular?
So nothing
about?
Basically, no fuzzers that I know of do what AFL does, and none of them come close to doing it as well as AFL does. But there are, like I said, a lot of domain-specific fuzzers, that are much more kind of controlled to a specific domain, like SQL injection RxS. There's also much less kind of clever fuzzers that don't use generic algorithms that you give, which are effectively just kind of brute forcers. You give it a character set and it runs through all of the permutations of that character set, which is a little more lame than like a program that figures out how to break another program. But yeah, so this thing is fast and fun. I like it. Thanks. Anyway, sorry.
This requires
Yes.
source code? Yeah.
To do it instrumented, yes, you have to compile it.
Okay, good. Yeah, good. Cool.
Cool.
Cycle's not there at the top, right?
That's it moving through its
Genetic cycles.
operation cycles. So it's doing a bunch of bit flips, and then it does a bunch of like arithmetic manipulation on anything it can interpret as a number. Then it does a bunch of just byte deletes, byte create adds. It'll like roll through, but it insert something in position 1, then position 2, then position 3, and then position 1 and. And it mixes deterministic modifications with genetic ones.
Let things run. Because usually we just let it run for a long time.
Yeah, so the idea is that you just let this thing go forever. And so you see like cycles done went back down, and the percent completion here will happily go up and down because what it'll discover a new path, and then it'll queue up a bunch more stuff that's going to go down that new path, and so your progress bar is just as dynamic as the growth of the algorithm. Which is, annoying, but not really a problem. You just kind of let it run for as long as you want it to.
Can you run AFL on AFL?
I mean, it takes a program as input. So
That's it.
you could compile AFL with AFL and then run it, the test case being a program that you would have run through AFL. Yeah, you could do it.